Finding the shortest subarray with the same degree looks like it needs checking every possible window. But there's a single-pass HashMap trick that gives you the answer in linear time. The degree of an array is the highest frequency of any element. Given an integer array, you need to return the length of the smallest contiguous subarray that has the same degree as the entire array. For example, with the array 1, 2, 2, 3, 1, the value 2 appears twice, and so does 1, so the degree is 2. The shortest subarray that still has degree 2 is just the two adjacent 2's, which has length 2. Your task is to compute that minimal length for any input array. A straightforward brute force would iterate over all possible start and end indices, build a frequency map for each subarray, compute its degree, and keep track of the smallest length that matches the global degree. That means 3 nested loops. The outer 2 choose the subarray boundaries, and the inner loop counts frequencies. The time complexity becomes big O of n cubed, while the extra hash map for each subarray adds big O of n space. For any reasonably sized input, this cubic blowup is completely impractical. The key insight is that for any value that achieves the global degree, the shortest subarray containing all its occurrences is exactly the span from its first appearance to its last appearance. So we only need to know, for each distinct number, how many times it appears, where it first shows up, and where it last shows up. We can gather all 3 in one left-to-right pass. We declare a dictionary for first indices, a dictionary for last indices, and a dictionary for counts. As we scan the array, if a number hasn't been seen before we record its current index as the first occurrence, we always update the last occurrence to the current index, and we increment its count. After the scan, we determine the maximum count, that's the degree. Then we iterate over the numbers that have that maximum count and compute the length of their span as last minus first plus 1, keeping the minimum. That minimum is the answer. You'll recognize this pattern when a problem asks for a subarray or substring that preserves a global property like maximum frequency, and the property can be satisfied by the extreme occurrences of a single element. Tracking first and last positions with a hash map turns a quadratic search into a linear scan. The algorithm runs in big O of n time because we make a single pass over the array and a second pass over the distinct values, both linear in the input size. The space complexity is big O of n in the worst case when all elements are distinct, since we store up to 3 dictionaries, each holding an entry per unique number. Try the next problem, same pattern. Subscribe for more linear time hash map tricks.